In today's video, we're going to review some of the concepts that we're going to need as we make our way through the trigonometry unit that we are starting. So today we're going to focus on the different angles that we're going to see and the parts to those angles as we make our way through the 4 quadrants on a coordinate plane. The first concept that we're going to look at is looking at angles in what we call standard position. So an angle is considered to be in standard position on a coordinate plane if the vertex of the angle is at the origin, or the point 0, 0, and the initial side is along the positive x-axis, and then the terminal side is going to be somewhere in one of the quadrants as we go around. And as we take a look, first of all, that initial side again has to go along the positive x-axis. So that is going to be the initial side. An angle has 2 sides, though. It has 2 rays. And so as we rotate in a counterclockwise direction like that, we can create an angle in standard position that would give us a positive angle. If, on the other hand, we decided that we wanted to go clockwise from the initial side and we rotate it that way, then that is actually going to give us a negative angle. But wherever we decide to rotate that second side, wherever it stops, that's where we terminate the angle, and therefore that side is called the terminal side. Now, before we get too far ahead of ourselves, we want to make sure that we know what the different quadrants are labeled. So again, starting from that initial side, as we rotate around in a counterclockwise direction, notice that we go from quadrant 1 to quadrant 2 to quadrant 3 to quadrant 4. And it would make sense that since we're doing a positive rotation in that direction, it would make sense that our quadrants are going in the order of 1, 2, 3, 4. So when we draw the angles when they are in that coordinate plane, as we go in the counterclockwise direction, which again is the positive direction, we also want to mark that we are going in that positive direction, because as you can see below, we have 2 angles that are actually look in blue. They look like they're exactly the same size, but they are giving us different angles depending on which direction we're going. So I just put a couple of very tiny axes on each of these angles where our vertex for the angle is now at the point 0, 0. And you can see that in both cases, those angles are both landing in the 4th quadrant. In fact, they could possibly even be landing in the exact same spot. So the terminal side could potentially actually be in the same spot, but yet they're going to be different angles. And so when you look at the one on the left, because we are rotating in that positive direction, we are going in from the initial side, we're going 90 degrees plus another 90 plus another 90 plus an additional amount, but not quite 90. So 3 90s gives us 270. That's going to be at this marking here, 270. And then we're going to be actually an angle a little bit more than 270. But on the right-hand side, we still are landing in that 4th quadrant. But in this case, because our direction is in the clockwise direction, we are getting a negative angle, and we haven't quite gone 90 degrees. So that angle is going to be some value between 0 degrees and negative 90 degrees. So we want to be able to draw these different angles in standard position. We always start out with drawing the initial side, so that's always going to be, again, along that positive x-axis. And then we determine, is it going to be a positive or is it going to be a negative angle? That'll tell us which direction our rotation needs to be, and it'll also help us figure out what quadrant the terminal side will be in. So since in A we want it to be 60 degrees, we are going to have some angle that's going to be in that 1st quadrant because we're going to be going counterclockwise. 60 degrees is going to be somewhere, let's say about here, And then we want to also show, and this is part of drawing it in standard position, you have to show with that arc and the arrow going towards that terminal side. You want to show that rotation, and then it's always a good idea to then write in that 60 degrees next to that arc. So in B, we've got 147 degrees. That again is a positive angle. So we're going to go again counterclockwise, but this time we're more than 90 but less than 180. So we're going to be somewhere in that second quadrant. So 147 degrees, that's close to 150 degrees. That's going to be, I would say, somewhere around here. But again, we still need that initial side. And then we want to show, again, because it's a positive angle, that rotation from the initial side to the terminal side is doing something like that. And that would be our 147 degrees. For negative 256 degrees, again, let's get that initial side going here. But this time it's negative, which means I'm going to go clockwise. It's more than 180, but it's less than 270. And so 256 in that negative direction, I'm going to say is somewhere, let's say around here in that second quadrant. And my rotation is going to do something like that. So again, that would be negative 256. And then for D, negative 315. Well, negative 315 is going to, again, be in that negative direction. So we're going to go clockwise from the initial side here. And 315, let's see if we go, 90 is here, then 180 would be here. That would be a negative 90, a negative 180. This would be a negative 270, so we have to keep on going. And negative 315 then is going to be roughly here, and showing that rotation in that negative direction, doing something like that. And again, that would be negative 315 degrees. So angles can be any amount of rotation, and they can go more than 360 degrees. If you think about a clock and the minute hand or the second hand, it's certainly, each of those are going to be going around the whole clock more than one time. So we can, for example, if you're looking at the second hand is going to go one full revolution or one full rotation in 1 minute. But if you do 2 minutes, then that second hand will actually go 2 full rotations around. So instead of doing a 360 degree rotation, you're actually going 720 degrees in rotation. So how do we show that that's what we're doing? Well, we end up doing from that initial side. If we are going more than one full revolution around, then we will be showing something like, let's say it is a clock, and we're going to be rotating around like this. So like this would be like 1 minute, and then this would be a second minute and a third minute, and each time we do a minute, we're doing an additional 360 degrees, and then let's say that it keeps on going for a little bit here, and then we end up terminating at a certain spot. Okay, and so that might be what our angle terminal side is, but to show that we are actually doing several rotations, we actually have to do this spiral in our motion for showing that rotation. Now, if you have a terminal side that is shared between a couple of different angles, we call those angles coterminal angles. So coterminal angles are going to be angles that end in the same spot. Okay, so they have obviously the same initial side, because the initial side is always the same, but they also are going to share a terminal side. And they've got an example here for, let's say, 390 degrees. That 390 degrees is going all the way around. This is going to be 360, but then we have an additional 30 degrees here, so that's why that makes that 390 degrees. But then we can also have just a rotation from the initial side to that same terminal side. and that's only 30 degrees. So 30 degrees and 390 degrees are coterminal. And really the way that you can find a coterminal angle then is simply to either add revolutions of 360 to an angle or subtract revolutions of 360 from an angle. So they just have to do multiples of 360 from wherever your terminal side is going to be, whatever that angle is going to be. So if we wanted to find one positive and one negative angle that are coterminal to the angles that we have here, if for 60 degrees, if we want to find a positive coterminal angle, all we'd have to do is add a 360 to that 60 degrees. So if we did 60 degrees plus 360, that would give us 420 degrees. So 420 would be coterminal to 60 degrees. If we wanted to have a negative angle, then we could take that 60 degrees and we'll subtract 360 degrees, and that would be a negative 300 degrees. So that also would be coterminal. In other words, 60 degrees, 420 degrees, and negative 300 degrees, they would all terminate on the same terminal side. So those would be considered coterminal angles. So then for B and for C, if you guys want to try those on your own and stop the video and then give them a try and then check it out, then that would be good practice for you. Otherwise, if you're not sure still how to do it, you can continue to watch. So for negative 150 degrees, we're already on the negative. If I add 360, that should tip me over to the positive side. So if we wanted a positive angle, we could take negative 150 plus 360, and that gives me 210 degrees. So that would be coterminal to a negative 150. And then to do a negative angle, I could just take that negative 150 and then subtract another 360 from it, and that would give me a negative 510 degrees. So that would be coterminal as well. For 400 degrees, to get another positive angle, I could add 360, but I could also subtract 360 in this case, because if I took 400 minus 360, that would still leave me with a positive angle. So I'm going to do that in this case, but I could have gone the other direction. I could have added and gotten 760. But I'm going to subtract. I get 40 degrees, so that's my positive angle. And now for the negative one, I can actually start it at 40 degrees because I know it's in the same spot as 400. And I'm going to subtract from that 40, I'm going to subtract another 360. Again, we're taking full revolutions that we're either adding a 360 or subtracting 360s from the original angle. So then 40 minus 360 would give me a negative 320 degrees. So that would be coterminal to both the 40 degrees but also to the 400 degrees. So for these next two problems, we want to find the angle of the least positive measure, not equal to the angle that's listed, that's coterminal with the angle. So since we are in A, we've got a positive angle and it is well above 360 degrees, we're going to have to subtract we're going to have to subtract 360 degrees and continue to subtract 360 degrees until we get an angle that's below 360, but still positive. So that's what I'm going to do in this case. And it looks like as I continue to subtract my 360s, I get myself down to an angle that is 26 degrees. That 26 degrees will be my least positive measure. That's coterminal to the 1106 degrees. So then for B, we've got a negative angle that we're starting with, and so since we want the least positive angle that's coterminal to it, now we're going to have to add 360 to that. So we're going to continue to add 360 until we get that first positive angle. And when I do that, I end up with 117 degrees. So that would be my least positive coterminal angle for negative 603 degrees. So let's quickly review some of our vocabulary around angles. We've got 4 different kinds of angles that we're used to working with. The acute angle, which is going to be somewhere between 0 degrees and 90 degrees. The right angle, which is exactly 90 degrees. The obtuse angle, which is some angle between 90 and 180 degrees. And then we have a straight angle, which is 180 degrees. Straight angle is basically a straight line. And usually when we are working with angles, we will use Greek letters to represent those angles. And the Greek letter that's most common is theta. Theta has this symbol to it. And so that's what we're going to see oftentimes as we're working through these problems. Now there is another type of angle that we will see, as we have already been working with, are angles that are greater than 180 but less than 360, and those are called reflex angles. And so if we have an angle that looks something like this, and we say that this here is theta, that is what we call a reflex angle. A couple other vocabulary terms related to angles that we're just going to quickly review are complementary angles. 2 angles that are complementary mean that they add up to 90 degrees. So let's say you have a right angle that's been cut into 2 parts. We know that the 2 parts added together would have to equal 90, and those are then considered complementary angles. Then we also have supplementary angles. Supplementary angles are 2 angles that add up to 180 degrees. And so if you had, for example, a straight angle that got split up into 2 parts, then when you add those 2 parts together, we know that they would have to add up to 180. So we could pretty easily figure out for these 2 algebraic type problems, we could figure out what x is because we know the relationship between the 2 angles on the left. They would have to add up to 90, and we know the relationship to the 2 angles on the right. Those 2 angles would end up being a straight angle, so they'd have to add up to 180. So those would be the equations that we would set up for each, and then of course we can solve those. If you'd like to solve those on your own, go ahead. Otherwise, here they are. And so once, of course, you find what x is, then you could always plug it back in and figure out what the actual angles are for each of those. And once you plug those back in, you can then, of course, check to make sure that what the relationship is actually holds true. Now we do have special angles that when they land on one of the axes, whether it's the x-axis or the y-axis, when the terminal side is on one of the axes, we call the angles quadrantal angles. And so we have quadrantal angles that would be at 90 degrees. So again, we've got our initial side, and then 90 degrees, and at 180 degrees, and then at 270 degrees, and at 360 degrees if we were going all the way around. And then any angles that are coterminal to them. So that would actually include a 0 degree angle as well. And again, if we were actually going to show each of these angles, for 90 degrees we would have to show the rotation there, and for 180 we would show that rotation. For 270 we would show the rotation like this, and for 360, of course, that would go all the way around. So one place that we can see where we would have rotations that are going more than 360 degrees, I already mentioned the clock, but anything that is circular, like a wheel that's going to rotate around more than one time, is also going to give us angle rotations that are greater than 360 degrees. So we have problems like this where we can actually use the concept of that multiple rotations to help us find, for example, a speed of an object like a wheel, but we can also figure out what the distance perhaps that a wheel has gone if we know certain parts of that information. So we got a couple examples here. We have a wheel makes 270 revolutions per minute, and the question is, through how many degrees will a point on the edge of the wheel move in 5 seconds? All right, so keep in mind now that we're actually looking at a couple of different units here for time. One is in terms of minutes and one is in terms of seconds. So we're going to use something that you guys have used in chemistry a fair amount, and that is dimensional analysis. All right, so I have some conversions that I'm going to be able to use in this problem as I do my dimensional analysis. One of them is that 270 revolutions for every minute. So I'm going to write my conversions over here. I'm going to have 270 revolutions in 1 minute. Okay, that many revolutions in 1 minute. That's one conversion. Notice that because I have seconds that I'm going to have to work with, I'm going to have to do some converting with our time units. And so I know that there are 60 seconds in 1 minute also. I also am going to have to work with degrees. So degrees are related to the revolutions. I know that there are 360 degrees in 1 revolution. Okay. And I think that's all I'm going to need. So what am I starting with? I'm starting with my initial condition of 5 seconds. So we're going to have 5 seconds to start with. And 5 seconds isn't 2 units that we're working with. It's just a singular unit. So it's going to be 5 seconds over just 1, because there's no additional units to it. But now let's start using the dimensional analysis conversions. So seconds, I don't want seconds. Remember, what I'm looking for is how many degrees. That's what I'm looking for eventually. So I just want degrees. So I have to get rid of seconds. So I'm going to use that there are 60 seconds in 1 minute. So I'm going to multiply by, I'm going to put my seconds in the denominator, and it's 60 seconds and then 1 minute on top. So with that, my seconds is going to cancel. And now I just have minutes. But remember, I don't want minutes, I actually want degrees. So let's see. Okay, here we go. Here's another one. So this one is 270 revolutions in 1 minute. So now I'm going to change to get rid of my minutes. I'm going to have 1 minute, and then I have 270 revolutions. And so my minutes unit goes away. And so currently my units that I have are revolutions, but I don't want revolutions. What I'm looking for are degrees. Aha, there is another conversion that I can use for that. 360 degrees are in every revolution. So I'm going to now multiply that by, let's see, I don't want revolutions, so it's going to be 1 revolution in the denominator to 360 degrees in the numerator. And so my revolutions go away. And now all that I'm left with as far as my units is my degrees. And that's what I'm looking for. So now that I have it in the proper unit, now I'm ready to do my multiplication straight across the top and straight across the bottom. And when we do the final calculations, we end up with 8,100 degrees. So that's in 5 seconds, that's how many degrees that point on the wheel will have rotated. All right, then we have a second example. It says, through how many degrees does a point on a wheel rotate in 5 minutes if the wheel is spinning at a rate of 225 RPM? So RPM is revolutions per minute. So why don't you guys give this one a try, pause the video, and then come back to it and check out how you did. Okay, so in this case we have 225 revolutions in 1 minute, but then remember we're looking for degrees, so we can also work with the conversion of 360 degrees are in 1 revolution. And the initial value that we're working with is the 5 minutes that we're going. So if we start out with 5 minutes, and then we try to eliminate the minutes for our unit, we can use the conversion of the 225 revolutions per minute. So the minutes cancel, and then we have to eliminate the revolution unit, and so we can work with the 360 degrees in 1 revolution. And again, having our dimensional analysis work for us, that will lead us to our final answer of 405,000 degrees. So we've covered the material for the 5-1 that you'll need to do your homework, but we are going to do a really quick preview for 5.2 as well. And the thing that we're going to be taking a look at in 5.2 is our right triangle trigonometry ratios. And we're going to see how those triangles are related to the angles that we've been drawing in standard position that we did for 5.1. So a couple of things that we're going to need for 5.2, just to do a quick review, is the Pythagorean theorem, which remember works for any right triangle. If you have a right triangle, we know that the sum of the squares of the 2 legs, A and B, is going to have to equal the square of the hypotenuse. So we know that A squared plus B squared is going to equal C squared for any right triangle. Also, when you guys learned about the right triangle trigonometry, that's SOHCAHTOA, that's working with our sine and our cosine and our tangent ratios between 2 side lengths on a right triangle. So for example, if we had the angles labeled A, B, and C, and angle A happens to have theta as the angle measure of rotation that it has, remember that for SOHCAHTOA, what that means is that the sine of an angle, let's say the sine of theta, is going to equal the opposite leg divided by the hypotenuse. And the cosine of theta would be the adjacent leg divided by the hypotenuse. And the tangent of theta is going to be equal to the opposite leg divided by the adjacent leg. And so if we were referencing angle theta, then this would be considered the opposite leg, this would be considered the adjacent leg, and the hypotenuse, remember, is always opposite the right angle. So this would be our hypotenuse. And so this is where our sine, cosine, and tangent ratios are located, and SOHCAHTOA was, again, a nice way for us to remember what those ratios are. And the last thing to touch on is something called Pythagorean triples, which you may or may not have heard of before, but it relates to the Pythagorean theorem. These Pythagorean triples are the lengths of the 3 sides of a right triangle, such that the 3 side lengths are whole numbers. And so you're probably most familiar with the famous 3, 4, 5 right triangle. So we could be looking at a right triangle that has, again, the 2 smaller sides would be the legs. So we might have a 3 here and a 4 here, and then the biggest side would be the hypotenuse. So if you did 3 squared plus 4 squared, that would equal 5 squared. So we could do that with all of these sets of 3 whole numbers, and we would have nice right triangles to work with. So you may become familiar with some of these more common, what we call Pythagorean triples. And that's it for today, and tomorrow we will continue our discussion of the section 5.2.